Okay, let's continue our discussion on linear regression. Today we'll focus on something called logistic regression for binary classification. So let's recall the setup. This is a similar setup to what we've been working with so far for binary classification. We assume that we have data pairs, xi and yi, where each xi is in Rd, and it's a covariate vector associated with an observation. And yi is then a binary class, which we'll assume is labeled +1 or -1, depending on which of the two classes the ith object belongs to. A linear classifier, as we've discussed last time, takes a vector w in Rd, as well as a scalar w0 in R, and it predicts the label associated with a particular observation to be the sign of the dot product between the covariate vector xi and w plus this bias term w0. Last time we discussed two linear classifiers. One was least squares, where we simply perform least squares directly on the labels, but we saw how that was sensitive to outliers and x. And also the Perceptron algorithm, which was an iterative method for doing linear classification, where we minimized an objective function. However, we saw last time that that approach had convergence issues and made assumptions about the data that weren't necessarily reasonable, such that the two classes are linearly separable by a hyperplane. We've already seen two examples in the last lecture of linear classifiers. One is least squares classifier, where we regress directly on the labels. However, we saw that that was sensitive to outliers in X. And also the Perceptron, which was an iterative algorithm for minimizing one particular objective function. However, we saw that that had convergence issues and made assumptions about the data that aren't necessarily reasonable, such that the classes are perfectly separable by a hyperplane. So in this lecture, we're going to see how we can extend the ideas from the Perceptron, combining it with probability, to fix some of the issues from the Perceptron. So this lecture is going to focus on something called logistic regression, which we're going to see is a fairly straightforward extension of the Perceptron. It's not going to be motivated that way, but the resulting algorithm will be something that looks similar to what we had with the Perceptron. So we're going to work with probability distributions in this lecture to fix some of the Perceptron issues. Okay, so we previously saw an example of a linear classifier that uses probability distributions in something called linear discriminants analysis, which is a particular case of a Bayes classifier, where we make the modeling assumption that the label is generated from a Bernoulli distribution, and then the associated covariates are generated from a class-specific multivariate Gaussian with mean equal to mu y, so a class-specific mean and a shared covariance matrix. Then, for a particular covariate vector x, we would want to predict the label for that x, and so we would be able to then use the log odds to do that. So in this case, the log odds is the log of the joint likelihood ratio, in which if the label of a 1 is more probable, this term will be positive. If the label of 0 or -1 is more probable, then this term would be negative. When we actually plugged in the distributions into these into this ratio and saw what was the decision, how were we making decisions, we saw that it amounted to a constant term, which we could call w0, plus the dot product between the vector x with a vector that we could call w, both of which had a very specific were a very specific function of the parameters of the model that we would have to learn or approximate in some way, for example, through maximum likelihood. So let's go back and return to the original formulation of what it is that led to our use of Bayes classifiers to begin with. If you recall, what we want to do is define a probability on a label for a particular observation given the covariates associated with that observation x. So equivalent to the log odds in the Bayes classifier, we could also say that we want to predict the label 1 if it's more probable than the label 0 given x. And to see how this is equivalent to the Bayes classifier using the log odds, simply remember from Bayes' rule that the probability of the label given the covariates is equal to the probability of the covariates given the label times the probability of the label, prior probability of the label, divided by the marginal probability of the covariates. And if we were to calculate the ratio for y equals 1 or y equals 0, this denominator simply cancels, and we have exactly what we have for the log odds of the Bayes classifier. If you remember, the reason we did Bayes classification is because we didn't know how to necessarily define this probability distribution, but we could define the conditional distribution on the covariates, the class conditional distribution, and a prior. So we were able to more easily come up with ways of defining those probabilities. So in this lecture, we're going to start from the log odds, and rather than define these probability distributions on a label conditioned on the covariate, we're going to start by defining the log odds directly. So let's motivate how we might directly define the log odds, and from that definition then be able to define a probability distribution on a label for an observation conditioned on its covariates. So if we classify x based on the log odds written this way, notice that this function L is going to become more and more positive the more confident we are that y is equal to +1. Simply by inspection, the more probable that y is +1 given x, the more positive this term is going to be. And as it gets more and more positive, we're more and more confident that y is equal to +1. The more and more negative it becomes, the more and more this ratio shrinks to 0, and therefore the log of that becomes more and more negative. The more confident we are that the label is going to be -1. And then in the case where this log odds is equal to 0, that's like saying we could go either way, because the probability of the label being +1 given x is equal to the probability of the label being -1. So this is the log of 1, which is 0. So in a sense, we want to directly define a function that has those properties that intuitively make sense, that becomes more positive the more confident we are when it's +1, more negative the more confident we are when it's -1, and the equal to 0 when we don't know anything. So last time we actually saw this function with a affine hyperplane, so separating hyperplane. We saw how the geometric interpretation of this function, the dot product between x and vector w plus some offset, can be viewed in this way, where the more x moves to the opposite side, one side of the hyperplane, the more positive it becomes. The more it moves to the other side of the hyperplane, the more negative it becomes, where this direction of this vector is determining which is positive and which is negative. So the vector points in the direction of becoming more positive. So as we go more and more in the direction of the vector w, the more positive it becomes. As it goes more and more in the opposite direction, the more negative it becomes. And all points along this line of the separating hyperplane are equal to 0. So in this sense, we already have a function that makes sense, that has the properties that we desire. And so we start from there when defining the log odds. So when we directly want to define the log odds, it makes sense to simply define it to be equal to the separating hyperplane representation that we've been discussing. So this is called a logistic link function, what we do is when we want to define a probability distribution on the label given the covariates associated with the observation, so when we want to define P of y given x, instead we start from defining the log odds to be equal to this. And we already know that this has the desirable properties, that as this becomes more positive, the more confident we are that the label is on one side of the hyperplane. As it becomes more negative, the more confident that it's on the farther it is on the other side, and so on. So the first question to ask is, what exactly is different from the previous Bayes classifier? Maybe it's an obvious answer, but recall that with the Bayes classifier, the linear discriminant analysis approach to Bayes classification, we had essentially this same exact representation, except we had a very specific formula for calculating the offset W naught and for calculating the vector W. And it was a function of the class priors, a function of the class-specific means, and a function of the shared covariances, the shared covariance matrix that's shared between each class. So there was a parametric form for how W and W naught were calculated, and because of the way, because of the values that those parameters can take, because of the way they're calculated those parameters through MLE, for example, there was essentially a restriction on what these two values could take, and perhaps it's a reasonable restriction, but still it's a restriction. So now the difference here between this representation and the Bayes classifier representation through linear discriminant analysis is that we're not going to put any restrictions at all on the vector W or the offset W naught. So we're going to let them be anything. So now when we want to actually calculate the probability of a label given its covariates and given the vector W and W naught, we can simply reverse or invert this equality by first plugging in for the probability of y being -1, 1 minus the probability of it being +1, then solving for this probability distribution in this equation to find that we end up with this, this definition. So what we've done here is we've come up with a way to directly define the probability that x is in class 1 given the parameters vector W and W naught. It's equal to this function, which is called a sigmoid function. So if we now interpret this function, we can see what's going on as this becomes much more positive. So as we're much more confident that the observation is on one side of the hyperplane, this numerator blows up to infinity, but then we have this denominator, which is 1 plus that same number. So this whole thing is converging to 1 as we become more confident that it's on the +1 side of the hyperplane. As this becomes more and more negative, so as x is moving more and more to the negative side of the hyperplane as defined by W and W naught, this numerator is going to 0 and this denominator is going to 1, so this entire thing goes to 0. So as x goes to more and more to the +1 side, the probability here is going more and more to 1 of the label being +1. As x is going to the negative side of the hyperplane, the probability of a +1 is going to 0. And when x is right on the decision boundary, this dot product is equal to 0, and so this is 1 divided by 2, and that uncertainty of which side of the hyperplane the observation is on is represented by a probability of 1/2 of each label. So that's simply showed here. What I'm showing, what this is plotting in the red line, is the sigmoid function as a function of the argument. So as it becomes more positive, we become more confident that the label will be +1. As the argument becomes more negative, we become more confident that the label will be -1. And when for all data points exactly on the decision boundary, we don't know which label it's going to take, and so that's represented with a 50-50 chance. Okay, so now we've motivated the sigmoid function as a way to map our observation, our covariates x, to a probability on a corresponding label. Let's now define logistic regression. This is the logistic regression classifier. Let's define it now from the start. So as we've done previously, purely for notation so that we write less, we're going to absorb the offset. So we're going to redefine the vector w to be the original vector where we attach the offset to the first dimension. So we increase it by one dimension. And we're going to define the covariate vector x now to actually have a dimension of 1s, which are going to interact with this offset. So the dot product of w with x is equal to the original function. It's equal to w naught plus the dot product of these two vectors. So again, we have labeled data. We have pairs x, y, where x is a covariate, y is its label. The labels are now going to be plus or minus 1. And so this is important for the way that we derive the algorithm in this lecture, that the labels are now plus or minus 1. It's more convenient to do it that way. Okay, so logistic regression then defines the model of each label conditioned on the covariate vector x to be equal to this. So we assume that all the labels are generated independently of each other. So given the covariate vector x and given the coefficients w, the data is entirely independent. And the probability for a particular observation, the probability of the label being plus 1, is simply equal to the sigmoid function, which we've discussed previously and motivated previously. So notice that what we've defined here is a discriminative classifier. So this is similar to some of the regression models we discussed that were also discriminative. We have no distribution on x anymore. We've only defined a distribution on y. The Bayes classifiers we've discussed previously are generative classifiers because we first define a distribution on y and then we define a class-specific distribution on x given y. So here again we're back to having no distribution on x. We only define a distribution on y. So in that sense, the logistic regression model can be viewed as a discriminative classifier.